We're looking at the second page of Worksheet 3. This is 9.7, 9.10 review. All right, let f be the function given by f of x, and let p of x be the fourth degree Taylor polynomial for f about x equals 0. Find p of x. So we want to find the fourth degree Taylor polynomial approximation, or the polynomial approximation. So we want to be able to build this polynomial using a Taylor rule. So what we're going to do is we're going to find our way all the way down to the fourth derivative, which will take care of this portion of each of the terms that we're working with. So we're starting off with f of x equals cosine of 3x plus pi over 6. Okay, let's go ahead and just find each of the derivatives all the way down to the fourth derivative. So the derivative for cosine of u is negative sine of u times u prime. So u prime is going to be times 3 there. The negative is coming from the fact that the derivative for cosine of u is negative sine of u. And then sine of u becomes cosine of u times u prime. So each time we're multiplying by the derivative of what's inside the parentheses. So that's why each term will keep multiplying. We'll have another factor of 3 multiplied to it. And then the derivative for cosine is going to be negative sine. So the negative turns to a positive, and then again times 3. And then sine becomes cosine times 3 again. So 27 times 3 is 81. And then cosine of u becomes negative sine of u times u prime. So times 3 again, negative 243. Now, we don't technically need the fifth derivative yet, but I just go ahead and found this. We're going to eventually need it, but we can come back and talk about the fifth derivative in a little bit. All right, so this is going to be Maclaurin polynomial, since Maclaurin series, since we have the center about 0. So I'm going to go ahead and evaluate each of the terms at 0. So plug 0 in for each of the x's. So cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is negative 1/2 times 3, so negative 3/2. And then cosine of pi over 6 is going to be root 3 over 2 times negative 9. And then we just go on down the line and find the derivative and make sure that we multiply by the coefficients. So third derivative evaluated at 0 is 27 over 2. And then 81 root 3 over 2. Okay. So here we have, all right, so all these terms will be just replacing the numerator of each of the coefficients. So the numerator for the first coefficient is root 3 over 2 divided by 1 factorial. So divided by 1 factorial, so that's not going to change anything there. X is going to be x is going to be at x will stay, and then the c is going to be at 0. So x minus 0 is going to be just x raised to whatever power we're dealing with. All right, so now we're moving on to f prime of 0. So that's going to be the first derivative. So my bad, we start off with the 0 when n is 0. So when n is 0, everything will cancel out to be just left with root 3 over 2. And then 3 over 2x will be for when n is 1. So the first derivative evaluated at 0 is negative 3 over 2. Negative 3 over 2 divided by 1 factorial over x times x minus 0 to the first power will reduce to be negative 3/2 x. And then we have the second derivative, so negative 9 root 3 over 2. So that replaces this, divided by 2 factorial. So when we divide this by 2 factorial, that's the same thing as, so there's going to be a 2 left over. So 2 times 2 will be 4 in the bottom. And then x minus 0 squared. Okay. Next up is 27 over 2 divided by 3 factorial. So that will reduce to be 9/4. And then 81 root 3 over 2 divided by 4 factorial times x minus 0 to the fourth power will give us 27 root 3 over 16. Right. So here is the work shown for dividing by the 2 factorial, 3 factorial, and 4 factorial. And then here's the resulting answer there. Part B, use the LaGrange error bound to show that the difference between the actual function evaluated at 1/6 minus the Taylor polynomial at 1/6, the maximum error will be less than 1 over 3,000. All right, so Lagrange error bound looks like this, where the remainder is going to be the derivative, n plus first derivative evaluated at z over n plus 1 factorial times x minus c to the n plus 1. Now, the center is at 0. Okay, we're told that the polynomial is centered at 0. We know that we're trying to evaluate f of 1/6, so x is 1/6. So if we plug this in here, Lagrange error bound, now the polynomial that we're working with is the 4th degree, so Lagrange error bound is for the n plus first derivative, so we'll be talking about 4 plus 1, or the 5th derivative evaluated at z, over 4 plus 1, so that's going to be 5 factorial. X is 1/6, c is 0, so 1/6 minus 0 to the 5th power. Now, our work is trying to figure out what will be the maximum value for the 5th derivative evaluated at z. So the 5th derivative, let's find the 5th derivative first. So the 5th derivative evaluated at 0, the 5th derivative not evaluated at 0, just 5th derivative, is going to be cosine of u, which we're working with the 4th derivative, so cosine of u times u prime. Cosine of u becomes, negative sine of u times u prime, so times 3, 81 times 3 is negative 243. So here's the 5th derivative, right? Now, we're looking to see what is the maximum value that this expression can take on. Now, if we think about all the values for x, we know that sine of 3x plus pi over 16, no matter how large this x gets, the maximum that this sine will be between negative 1 and 1, right? Sine curve will just keep oscillating between negative 1 and 1, which means that there's not going to be any value greater than 243, because 1 will be the maximum, 1 and negative 1 will be the maximum absolute values of this. So because it oscillates between negative 1 and 1 and back and forth, we know that this negative 243 can't get any larger than this. The most that it can do is it will be less than 243, because you're multiplying by fractional values less than 1. But as soon as it hits 1, that will be the maximum value. So we know that the 5th derivative will have the maximum value of 243. There's no way that it can ever get greater than 243. So that'll be a safe upper bound. So 243 will be a safe upper bound for the 5th derivative value at z. We're trying to find out what is the ceiling, what is the maximum ceiling for the error, and we want that maximum ceiling to be less than 1 over 3,000. So the ceiling for the error is 243 over 5 factorial 1/6 to the 5th. So now this value, this needs to be less than 1 over 3,000 if we want to show that this is a true statement. So if we use our calculator, 243 over 4 factorial times 1/6 to the 5th is 0.0002604, which is less than 1 over 3,000 if we tested this with our calculator. All right, number 4 here, 3rd page. Taylor series for about x equals 5 for a certain function converges at f of x. The nth derivative is given here. Okay. Now show that the 6th degree Taylor polynomial for x equals 5 approximate f of 6 with an error less than 1 over 1,000. So we're trying to find, we want to find the maximum error for the 5th degree polynomial. So we want to show that the 6th degree Taylor polynomial will approximate f of 6. So the 6th degree polynomial, if we want to find the error for the 6th degree polynomial, we're going to have to work our way down to the 7th derivative evaluated at z. So then the 7th derivative evaluated at z will have to be using this formula here. So negative 1 times, so we know that this value will be 5 factorial over 2 to the 5th times 7. Okay, since we are increasing our value to be 7. So we know that this expression will be for the 7th derivative evaluated at the maximum value that it can be, will be this value here, divided by 7 factorial, right? Since that's the rule for our error bound. X minus c, so 6 minus 5 to the 7th. And then if we plug this in our calculator, it's 1 over 9408, which is less than 1 over 1,000. Okay, number 5 here. We're trying to approximate the 4th degree Taylor polynomial about x equals 1. The maximum value for the 5th derivative between 1 and 3 is going to be 0.01. Hey, that is that the 5th derivative evaluated x cannot be greater than 0.01. Then the maximum error incurred by using this approximation to compute f of 3 is, so we want to use the 5th derivative to show the maximum error for the 4th degree Taylor polynomial. So if we want to find the error for the 4th degree polynomial, we have to work our way down to the 5th derivative. So the 5th derivative evaluated at z over 5 factorial times x minus c. X is 3. X is 3. And it's centered at 1, so that's going to be c. C is 1. So that'll be 3 minus 1 to the 5th, since everything is evaluated at the 5th 1 degree higher than the 4th degree. So we know that the 5th degree evaluated x cannot be any greater than 0.01. So I can replace this value with 0.01, and then we just simplify this expression and see if this error is less than or the maximum error for this, which will be 0.00266. Okay, last page. Okay, what are the values for x for which the series will converge? So we want to go through ratio test. So ratio test, limit as n approaches infinity. So a sub n plus 1 divided by a sub n. So a sub n plus 1, replace each of the n's with n plus 1, divided by a sub n. Same thing as multiplying by the reciprocal. And if we clean this up, we have x over n plus 1. As n approaches infinity, this expression will go to 0, since x will just stay at a constant. So 0 is always less than 1. So that means our interval of convergence, that the series will always converge for any values of x. So negative to positive infinity. Okay, number 7, the coefficient of x to the 6th in the expansion for f of x equals sine of x squared is. So how about let's go ahead and build our Maclaurin polynomial for sine of x. So sine of x is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. We want to make sure that we memorize these basic Maclaurin series. And now we can build the sine of x squared by plugging in all the x's with x squared. So x becomes x squared, x cubed becomes x squared cubed, which is x to the 6th. X to the 5th becomes x squared times to the 5th, which is x to the 10th. And then x to the 7th becomes x squared to the 7th, which is x to the 14th. Now we're looking for the coefficient for x to the 6th. So notice that the x to the 6th is now this term. So the coefficient will just be 1 over 3 factorial, negative 1 over 3 factorial, which is negative 1/6. Okay, we have f prime being sine of x squared. Then the coefficient of x to the 7th for f of x would be, so let's see, f prime of x is sine of x squared, which if we expanded would be from above here, x squared minus x6 over 3 factorial plus x to the 10th over 5 factorial. Now we want to find the f of x from f prime. So to get to f of x from f prime, we need to find the indefinite integral. So the integral of f prime is same thing as finding the integral of x squared minus x to the 6th over 3 factorial. So x squared, the integral for x squared becomes x cubed over 3. the integral for x to the 6th over 3 factorial becomes x to the 7th over 6 times 3 factorial. Sorry, x to the 7th times divided by 3 factorial times 7. So now this is the term that we are interested in for x to the 7th. Now the coefficient for this expression would be -1 over this entire denominator. So -1 over 3 factorial times 7. So 3 factorial is 6. 6 times 7 is 42. So -1 over 42 will be the coefficient that is for this x to the 7th. So therefore answer D.